So this is section 9.3, molecular shape and polarity. So let's review just a little bit from chapter 8. Here's somewhat of a Lewis electron dot structure of carbon dioxide. And we learned in chapter 8 that when two atoms of differing electronegativity combined, the bond unequally shares electrons. This is because there's a difference in electronegativity. Carbon has an electronegativity of 2.5. Oxygen has an EL of about 3.5, I believe. And so there's a complete 1 difference in electronegativity, and electrons would be pulled towards the oxygen, and we'd illustrate that with an arrow like this, showing that this would be more positive and this would be the more negative area, and we could actually use like the Greek partial letter delta right here, meaning partial negative charge here and a partial positive charge right here. And so this direction right here would make it be partially negative over here and partially positive right here. These are called a dipole, meaning that there's two poles, a positive pole and a negative pole right here. And this is also called a polarized bond or a polar bond, or the fancy name for this arrow right here is called a dipole moment because it has a charge in a given direction. In physics, you'll know that that's called a vector quantity. Well, now in this chapter, we're going to do a little more with this. We're going to do more with this other than just identifying the polar bond. Because now that you know shapes, now that you know molecular geometries, you can take two things into account. For an entire molecule, we need to consider two pieces to decide its molecular polarity. Number one, we need to look at the polarity of the bond, which we just talked about right here and drew the dipole moment, or noted that it was polar or polarized. And then number two, we need to take into account the geometry of the molecule. So its actual shape. Is the shape linear? Is it trigonal planar? Is it bent? What is that molecular geometry? Because that's going to help us determine whether throughout the entire molecule is there an area where it's more negative and more positive, or do they even out? And are they perfectly symmetrical and therefore a non-polarized molecule? I'm going to take and move this, and then we'll slide this paper over, and then what we'll do is we'll go on to the next page, because bottom line throughout this portion right here, we want to be able to answer the question, is a molecule polar or not? Is it polarized throughout the entire molecule? Is there a positive and a negative area? We could draw a dipole moment throughout the molecule, and that would indicate where it's more negative and where it's more positive. Which long term, when you're looking at that, if a molecule ends up having a part that's more positive and a part that's more negative, now all of a sudden it's like all other chemistry. Positive and negative things would attract, and that's what causes molecules to stick together really good, or maybe not stick together so good. So let's go back to the carbon dioxide that we drew over here again. Here's a little better Lewis dot structure, and here are the dipole moments going both directions. Looking at it from a shape piece, this has a 180 degree bond angle because we have two electron domains right here, both bonded, and it's called linear. So taking both of these pieces into account, we have a linear molecular geometry, and we have two polar bonds, one going this direction, one going this direction. Now, the trick is to look at the symmetry of the bonds. If the shape ends up being, if the molecular geometry ends up being where the polarized portions are equal and opposite of one another, then we would say that the geometry and bond polarization are symmetrical, and we call it a non-polar molecule. So this would be a not polar molecule, even though we have a polar bond inside of here, two of them as a matter of fact, polarized bonds because they have an uneven distribution of electrons. They symmetry one another or balance each other out throughout the molecule due to its linear 180 degree shape. So, answering the question, polar or not, this is a not polar molecule. So we're going to spend the rest of this video now just doing examples of polar and nonpolar molecules and how to determine them using two pieces. First of all, the polarity of the bond. Second of all, the geometry of the molecule. So I'll take this paper and I'm going to move this one away. I'll leave these ideas up right here. And then we're going to play the game polar or not with several molecules, and we'll take a look at them from the point of view of bond dipole and geometry of the molecule. So let's look at this one first, HCl. So first of all, take a look at the bond right here. Is there a difference in electronegativity between hydrogen and chlorine? Well, you don't actually have to look that up. You can just look at them on the periodic table and see that they're far apart from one another. And yes, there is. And so this bond right here is going to be a polar bond. And so on here I could draw a dipole moment from the more positive one to the more negative one. And I could put a little partial negative charge over here and a little partial positive charge right here. And we know that that's the direction that the electrons are unevenly shared. Now, the second piece I have to take into account is the geometry of the molecule. Well, we only have two atoms right here, and 2 bonded and 0 non-bonded is called linear. So this is a linear shaped molecule, and it has 180 degrees, because that's the only thing that it can be. And so we can see that throughout here, we definitely have an uneven distribution of electrons. It's going to be more negative over here in this part. It's going to be more positive over here in this part. And so we would classify this as a polar molecule, or a molecule that contains a dipole moment, an overall uneven distribution of charges throughout the molecule. And that's what makes HCl's stick really good to other HCl's, is because we got a partial negative charge here, and if we see another HCl molecule in that solution or in that sample of substance, this negative would attract to this positive right here, and that's what makes the molecules stick together really good. All right, let's look at a second one, NH3. So in this one, first of all, we notice that there's an uneven distribution of charge just in each bond. From the hydrogen to the nitrogen, we'd have an electron pull, because of course hydrogen and nitrogen have a different electronegativity than one another. We could draw those for every single one of these. But then let's look at the shape. We have 1, 2, 3 bonded, 1 non-bonded. And so this one is from the family of tetrahedral, but it's called Trigonal Pyramidal. And in a trigonal pyramidal, remember, this bond angle is reduced to about 107 degrees from the 104.9 degrees, which means that these hydrogens right here are actually in effect like squished together a little bit more, and we have this exposed area of unshared electrons right here that's going to have a very negative charge throughout the molecule, because remember, we're going to have arrows pointing all this direction right here, pulling electrons to this area. And then we're going to have more of a positive area where these hydrogens are right here. And so we do have an overall dipole moment throughout the molecule, and this molecule is called polar. All right, so we've had two polars. Let's see if we're going to find out any nonpolars in here. Here's another example right here, CCl4, carbon tetrachloride. So carbon and chlorine obviously have different electronegativity, so we would have a pull this direction. We would have a pull for electron this direction. Whoops, I'm drawing it backwards. Sorry. It should be positive here and negative out here, because obviously chlorine is further to the right than carbon is. And so chlorine has an electronegativity of about 3, carbon's about 2.5. So let's turn this arrow around. The arrow would go this direction. We'd have a plus sign right here. Let's draw this one correctly. Plus sign right here, going here. Plus sign right here, going here. All right, so we do know that we have polar bonds inside of here. Uneven distribution of electrons between each one of these because they have different electronegativities. Now let's look at the shape. 4 bonded, 0 non-bonded. This is called a tetrahedron. And a tetrahedron or tetrahedral shape has a 109.5 degree bond angle. The bond angles would be all identical in 3 dimensions, all around one another. And so we'd have a pull for electrons this way, equal opposite pulls in every single direction. And so since the dipole moments, or the pulls for electrons, equal each other out, we would say that this is a nonpolar molecule. Now, the bonds are still polar bonds. They're polarized. But overall, the molecule is not polar because we have a symmetrical shape. Symmetry is the key to really determining the polarity of molecules. All right, let's look at this one. Water right here. We'd have a pull for electrons this direction, pull for electrons this direction. Definitely polar bonds right here. Two bonded, two non-bonded is called bent. And remember, bent has a bond angle of 104.5 degrees. These guys are squished together a little bit. Very negative charge up here on the oxygen. And this is definitely a polarized or polar molecule because we have an uneven distribution of charge throughout the molecules because it is not symmetrical. Now, somebody might try to trick you someday, and they would draw water like this. They'd draw water O, and then they'd put an H right here, and they'd put an H right here, and an unshared pair here, and an unshared pair here. It looks perfectly symmetrical, and you'd say, oh yeah, there's a pull for electrons this direction, and there's a pull for electrons this direction, and they even each other out. But what you didn't realize is that this is drawn in 2 dimensions, and remember, we live in a 3-dimensional world, and so we would have 1, 2, 3, 4 electron domains around it, 2 bonded, 2 non-bonded, and therefore it would be a bent shape, 104.5 degrees, and so it would be asymmetrical completely. Last one right here, this guy, I'm just going to pull these up on the screen right here to the left because they have some nice space-filling models of them. Here is the CCl4. I'm sorry, yeah, the CCl4 right here. This is the one we looked at right over here, and you can see that the electron electronegativities are given 2.5 for carbon, 3 for the chlorine. You can see that the electron domains are, the arrows right here all even each other out, the dipole moments. Now, this guy right here, we can see has a chlorine sticking off the top. We'd have a tetrahedral shape, 4 bonded, 0 non-bonded. Bond angles would all be the same, but we'd have a pull for electrons this direction because the electronegativity of chlorine is 3.0 versus carbon, which is 2.5, and hydrogen, which is 2.1. So we have an overall pull for electrons this way, and this molecule would be classified as polar. All right, lastly, after all those examples, let's make sure that we've got some words straight. So a polar molecule is something that has a positive and a negative charge unevenly distributed throughout it. We use an arrow like this throughout the molecule indicating the more positive area here, the more negative area here, and a partial negative charge is with this small Greek letter delta and a negative sign, and a partial positive charge with the Greek letter delta like this with a plus sign. We call this arrow, which has a magnitude and direction, a dipole moment. These are what are called polarized molecules. That's another way to say a polar molecule is a polarized molecule, or the molecule is polarized. What does it mean to be polarized? It means there's an uneven distribution of electrons throughout the molecule, either because they're polar bonds, but mostly because the polar bonds are asymmetrical. There are positive and negative portions to the molecule. The molecule is asymmetrical with respect to the distribution of positive and negative parts. All right. Good luck with your molecular shape and polarity.